Researchers from the University of Toronto Engineering and King Abdullah University of Science and Technology have overcome a key obstacle in combining the emerging solar harvesting technology of perovskites with the commercial gold standard silicon solar cells. The result is a highly efficient and stable tandem solar cell, one of the best performing reported to date. Like silicon, perovskite crystals can absorb solar energy to excite electrons that can be channeled into a circuit. But unlike silicon, perovskites can be mixed with liquid to create a solar ink that can be printed on surfaces. The ink-based manufacturing approach, known as solution processing, is already well established in the printing industry and therefore has the potential to lower the cost of making solar cells. Adding a layer of perovskite crystals on top of textured silicon to create a tandem solar cell is a great way to enhance its performance. But the current industry standard is based on wafers, that is, thin sheets of crystalline silicon that were not designed with this approach in mind. Though they may look smooth, standard silicon wafers used for solar cells feature tiny pyramidal structures about 2 micrometers high. The uneven surface minimizes the amount of light that reflects off the surface of the silicon and increases overall efficiency, but also makes it difficult to coat a uniform layer of perovskites on top. Most previous tandem cells have been made by first polishing the silicon surface to make it smooth and then adding the perovskite layer. That works, but at additional cost. This research team took a different approach. They increased the thickness of the perovskite layer, making it high enough to cover both the peaks and the valleys created by the pyramidal structures. The team discovered that the perovskites in the valleys generated an electrical field that separates the electrons generated in the perovskite layer from those generated in the silicon layer. This type of charge separation is beneficial because it increases the chances that excited charges will flow into the circuit rather than other parts of the cell. The team further enhanced the charge separation by coating the perovskite crystals in a passivation layer made of 1-butanethiol, a common industrial chemical. The tandem solar cells achieved an efficiency of 25.7% as certified by an independent external laboratory in Germany. This is among the highest efficiencies ever reported for this type of design. They were also stable, withstanding temperatures of up to 85 degrees Celsius for more than 400 hours without a significant loss of performance. Industry can apply this without having to make costly changes to their existing processes. The researchers are continuing to work on improvements to the design, including increasing stability up to 1000 hours, one industry benchmark. And they are saying that their approach opens a door for the silicon photovoltaic industry to fully exploit the great advances perovskite technology has made so far.